We're about to start a new section of electromagnetism, and first we have to look at magnetic field lines. I'm going to be looking at magnetic field lines around permanent magnets and also around current conducting wires. Now when we look at current conducting wires, that's the first time you're going to see how a current can create a magnetic field. In other words, movement of electrons creating a magnetic field, electromagnetism. But first, let's look at something hopefully very familiar to you, and that is the magnetic field lines around a permanent magnet. So what's used to see, the first question is, what is used to see a magnetic field line? And hopefully most of you know iron filings, but I also want to remind you of two other elements that are magnetic. And if you can find yourself a periodic table, I want you to notice that iron, cobalt, and nickel are all in a row, side by side on the periodic table. And these are the three only elements that have just naturally around them or can be induced to have a magnetic field. And so it's not just iron filings. The answer is iron filings, and oops, I've got to get that turned on. Iron filings, as well as cobalt or nickel filings will align with magnetic field lines. All right. What do you notice about the strength of the field at various points? Where is the field strongest? How can you tell? All right. If we look at the first image with the red and blue magnets, you can clearly see that most of the iron filings have accumulated at the poles of the magnet. Always the magnetic field is most intense directly at the poles of the magnet. And as you get further away from the poles, the field lines spread out, and on the sides of the magnet, they create almost like a loop or a bowed and effect around the magnet. And you'll notice that the field lines are further apart than they are right at the poles. So wherever the field lines are closest, we have our strongest field. So the answer is at the poles, the field lines are closest together. Therefore, the field is strongest here. All right. Is the real magnetic field two-dimensional? No. We have to put the iron filings on a piece of paper, which makes it two-dimensional. But if you are able to look around a magnet, it's a three-dimensional magnetic field. So the answer is no. The field is three-dimensional around the entire magnet. All right, now I'd like you to look at the diagram below. This is going to be important for the next question. And I want you to notice that inside the magnet, the field is running from south to north. But outside the magnet, it's running from north to south. So field lines always exit the north and enter the south. And the only way you could get the field exiting the north is if the field ran south to north inside the magnet. So when we look at our next question here, what do you notice about the field direction at various points around the magnet? So the field lines run south to north inside the magnet. Then when they exit the North Pole, they loop around to enter the South Pole. Field lines always exit the north and enter the South Pole. And often you have to draw field lines on diagrams, so it's important that you know very clearly in your mind they exit the north, enter the South Pole. All right, which of the following is correct? Well, whenever fields attract each other, you should be showing the lines connecting. Whenever they repel each other, you should be showing fanning out of the field. So we know north and south attract each other, and therefore we should be drawing the lines connecting. The question is, which of the diagrams, B or D, are showing the field lines in the correct direction? So take a moment to look at it, and hopefully you selected B, because fields always exit the north and enter the South Pole. Now, comment on your answer. Field lines that show attraction always connect, and magnetic fields always exit the North Pole and enter the South Pole. All right, take a close look at number 6, remembering those rules, and see if you select the right image. So I'll give you a moment. Hopefully you selected answer D, showing a connection between the fields, and that your field exited the north and entered the south in both cases. All right, now we're ready for the next page. And this is the final question about magnetic fields around permanent magnets, and we're I'll end the video on question 7. So it says here, draw the magnetic field lines between a spherical piece of non-magnetized iron and a magnet whose north pole is placed near this piece of iron. Now, it's important that you know that when you have a non-magnetized piece of iron, that the iron atoms are able to align themselves to a magnetic field. So even though this piece of iron, and hopefully you all know that not every piece of iron is magnetized. Hopefully you realize that there are pieces of iron that have no magnetic field to them. And so we're going to draw a sphere here and then draw ourselves a permanent magnet with the North Pole placed near the iron ball. Oop, sorry. That technical difficulties here. Need to erase that. Scroll back up. All right. And the South Pole there. Now what's going to happen is that the field lines are coming out of the North Pole. And I told you that the atoms of iron inside this ball are going to align themselves with the magnetic field of the permanent magnet. This means that they're going to be running in this direction. So if they're exiting the ball on that side, remember magnetic field lines always exit the north and enter the south, which is why this ball is going to get attracted to the magnet, because we have created a south pole in that sphere. Now you should also show a looping around so that the field lines enter the South Pole. And you might show more than one. And that's what you would need to do for that problem. And I'll see you in the next video.